Okay, I thought I'd make a really quick review. Now, this review is for Physics Chapter 3, High School Physics. We're going to cover a couple of subjects. Actually, we're going to cover 8 subjects, 7 and 1 exercise. We're going to first cover Newton's law. We're going to add vectors. We're going to talk about Newton's second law, the fact that mass does not equal weight. We're going to cover free body diagrams, and then free fall. Then we're going to cover Newton's third law. Of course, after that, we're going to do a couple of exercises that are a little more challenging from your book. Okay, so let's go ahead and get started. Number 1, probably the most important concept, and it's really simple, so we're not going to take that long on it, and that is the concept of inertia. Okay, and in general, in high school physics, inertia equals mass. That's about it. It's not really that much, but you always want to keep in mind there's 3 really important rules. Objects in motion tend to stay in motion. Objects at rest tend to stay at rest. And if the velocity is unchanged, it stays unchanged. When your velocity changes, then you have an acceleration. Now, before we talk about accelerations, though, we have to talk about vectors. In vectors, we really care about 2 things that we can do with vectors. One, adding vectors using the parallelogram rule. Now, the parallelogram rule is really quite simple. It's whenever you add 2 vectors, add them head to tail to form a parallelogram, and then you join them, and that's going to give you the resultant vector. Okay, let me show you with a little diagram here. Okay, so we have this one blue vector, and then we have a green vector, and as you notice, we add the other sides that would make it a parallelogram. Okay, and remember what parallelogram means. Okay, so there should be no confusion about this if you understand your geometry a little. And then we add the tail of both to the head of both, and that gives us our resultant vector. Now, let me go ahead and give you another example, just in case this one wasn't clear enough. If we make this little slanty here, like that, and then this one slanty, and they're not at 90 degrees, they don't have to be at any, they can be at any angle you want. Just make sure that your greens and your blues are parallel, and your resultant vector will be the result of the tails to the heads. Okay, so now the second part, this one's a little more challenging, and you're not going to see it that often, but in the future, if you plan on more physics, you're going to see this way a lot, so get used to it. This is the simple version too. So the Pythagorean rule just basically tells you, if you have 2 orthogonal, and that's a fancy word for at 90 degrees, orthogonal vectors, you add the square of each to get the hypotenuse, which is the resultant vector. Okay, so let me give you an idea of what this means. You've seen, one of your problems actually had something like that, so I thought you might want to understand it. Remember, if you understand beyond what you're being shown, that's actually going to give you an advantage to understand the basics that you should be tested on. Okay, so let's assume that we have these 2 vectors. This vector is about length 4, and then we're going to have a little green vector down here, and this vector is of length 3. Really simple example. Now, this should be clear that the Pythagorean rule would tell us that the red line here that is connecting these 2 will be the hypotenuse, and we can get that length. But if you can test it out geometrically, and you'll find out that the rule here, this other vector here, will also be exactly the same thing. So we can use that little trick of geometry to figure out what our resultant vector would be. So this is going to be 16, and this is going to be 9. And so our resultant vector will be the square root of 25. So obviously, this vector here is going to be of length 5. Now later on, we're going to talk about how to get the angles there, which is the sine of the angle and the cosine of the angle and stuff like that. But let's not worry about that right now. Let's go to Newton's law, the second law. And that is, of course, the most famous law, and you should have that tattooed on the back of your hand. Actually, don't do that. And that is the sum of the forces equals mass times acceleration. Now remember, this is telling us a few important things, and always remember this. Repeat this to yourself until you are tired of saying it. The force is proportional to the acceleration, and if the acceleration is unchanged, I know I didn't put the F there, sorry about that. If the acceleration is changing, so does the force. But if the velocity is constant, acceleration is 0. You need to write these things down, by the way. Don't just read this thing blindly, okay? If you're not writing it, you're not getting anywhere with this stuff. Okay, so if the acceleration is 0, so the sum of the forces, of course, what does that mean? Well, for high school physics, by the way, keep this in mind. Your acceleration is usually either constant or 0. So later on, we'll talk about changing accelerations, things like that, like with springs and stuff, but right now, let's just keep things simple. So now let's go ahead and mass, and of course mass, just remember that mass is a measure of matter and it has inertia, whereas weight is a force. So by the second law, weight is the product of mass and gravity. Now I mistyped it there, so I'm going to just cover it up here with my little there, so that's why the text looks a little different for mass and gravity. So mass is measured with a balance, whereas weight is measured with a spring type of scale. And in case you forgot what these things are, well, the spring scales, my drawing skills are terrible. It's but hopefully you get the idea. Your balance is one of these things here. That's a balance. And scale, when you go to the grocery store and you're going to go buy vegetables, you see one of these things where it's got the big bowl at the bottom, and then it's got this number dial up here. And of course, this is a scale. Okay. So that's easy enough. Okay, so that means that weight includes mass, but not the reverse. Now, on Earth, weight can change. For example, if we measured somebody that weighs that has 100 kilograms of mass, that means that they would weigh 980.665 newtons at the North Pole. Yet, curiously enough, at the equator, they'd only weigh 977.275 newtons. It's a tiny difference, really. That's why we don't really bother with it most of the time. That's less than 1% light. And that's really because of the fake centrifugal force. I just call it centrifugal force because unless most non-scientists understand what it means, but scientists will tell you this is fake. It's not a real force. Let's worry about that a little later, but at least for now, we'll just understand that it's a fake force, okay? So let's go ahead and continue. So free body diagrams. Most important thing about your free body diagrams, okay, is you have to draw everything here. You don't have to be an artist. I mean, look at my horrible drawings. I mean, they don't really, maybe you'll think yours are worse. Doesn't matter. As long as it gets the idea across. Just make sure that you're getting the idea across. And if you draw enough of these, pretty soon you'll be Da Vinci with this stuff. Part of why I'm so terrible is because I'm drawing on a tablet. So anyway, so here's a second type of diagram. I just thought I'd show you when you're drawing. Like I said, you can draw all kinds of diagrams. So in this case, I'm drawing this guy up here. He's pulling up this box. And if you're going to pull up a box, now notice, whenever we draw our forces, and that's what your diagrams are for, you're supposed to be drawing them for the forces. Our tension, which is a force, is based on the center of gravity, or center of mass. Okay? So here we have our two forces. And remember that, draw from the center of mass. Okay? And this is for forces. You can draw other things, but really, at your level, you really want, and yeah, I did this wrong, so I correct myself there. Okay. So let's go ahead and cover freefall next. Now, in freefall, you have to ask, should we account for air resistance? And the question is going to tell you. If it says yes, then you should know that the object will eventually reach a terminal velocity, and that is because it has an opposing force on it. If we do not account for air resistance, then the object will speed up until it hits the ground. Now, in real life, that's just not going to happen, but in physics, many times they'll tell you to ignore air resistance. So check that out. Just keep those two things in mind. Okay? Now next, for friction. Now remember that friction is a force that opposes your motion along a surface. So I thought I'd show you a fancy little diagram that many of you will probably not work on too much yet, but in the near future, we'll talk about this a whole lot more. And that is when we have a box sliding down an inclined plane. So if we did, and we were pushing on it, we would have a force going up. This red here would be the force of friction, and this little green arrow here would be mass times gravity. And then we would have to actually calculate, this is the normal force, Okay, and the normal force. And these are our two components, by the way. I'm breaking down our green arrow into its two vector components. And when we break them down, this one is based on mg sine theta, and this one is mg cosine of theta. You remember those trig symbols. You're going to see a lot more of them in the future. And that's theta. And by way of a couple of trig tricks, you should verify that that is true. So that's our vector addition. Let's go ahead and move on to Newton's third law. Okay, so as you know from Newton's law, it just tells you that for every force object A exerts on object B, object B exerts an equal and opposite force on object A. And keep that in mind, what I put in bold. Always draw your force diagrams. This is where it's even more important. And of course, remember, complementary forces never act on the same body. Now, sometimes people will give you tests, and they'll give you tests to try to see if you know this fact. So do not forget that the complementary forces do not act on the same body. Okay, it's counterintuitive. So let me go ahead and try to show you just by the simplest of diagrams. Here you got our friend here. And our friend has the force of gravity, and that is Earth on human. Well, let's just write. And here's the one from human on Earth. And remember, these forces are exactly equal and opposite. So this is Earth on human, and this is human on Earth. Okay? There we go. And the normal force, by the way, it's also a third law force. It is the result of mg cosine theta, if you look at that diagram. So remember, this is counterintuitive. If you think you know it, you probably are going to fail it. So please, draw these diagrams, draw them in different ways so that you can get a better idea, okay? But to give you another, another quick example, we're going to draw a little buddy here with who's about to step forward on top of a skateboard. Now, here we go. No, okay, yeah, my perspective is terrible, but these are just, like I said, I'm not trying to be an artist here. Let's just draw the head for reality's sake. And just two stick arms. Okay, now, if you're stepping back, if you're going to step forward, the force you put on the skateboard is actually the red force, stepping back, and the skateboard is actually going to have this direction. So this is the human on the skateboard, and this is the skateboard on the human. Now here's something funny. So if the skateboard has no friction, okay, then the green arrow is going to be too small, and the net force will be non-zero. What does that mean? Well, it's going to go backwards, and you're going to eat dirt. You're going to be a very unhappy person. That's why you shouldn't be walking on skateboards. Sorry about that little hiccup there. Anyway, okay, so we've got a couple of problems that I'm going to leave you, and I've already got the solutions in the next video, and I will post it later on in the afternoon. So in the meantime, here's the problems. Now, you've already seen them in the book. This one you've seen in the book. The next one is my variation on one of the problems. So in this case, we have a mother of mass 50 kilograms and her daughter of mass 25 kilograms are ice skating. They face each other, and the mother pushes on the daughter such that the daughter's acceleration is 2 meters per second squared. So what is the force exerted by the mother on the daughter? What is the force exerted by the daughter on the mother? And what is the mother's acceleration? Okay. Now, for this, don't forget to draw the picture. Don't forget that Newton's third law and second law will be applied. And don't overthink it. Honestly, if you're starting to go really crazy, you're trying to invent relativity or something like that, you're probably doing too much. This isn't that hard. You just haven't seen it enough times. Now, here's the second example. So this one, Albert's mass is 75 kilograms. And he decides to test how fast an elevator accelerates by taking a scale with him and weighing himself during the first few seconds that the elevator is rising. Now, since this is fantasy land, we can assume, 1, that the elevator keeps accelerating, and 2, that the gravity is 10 meters per second. So we want to know two things. How much does Albert weigh? And if the scale reads 975 newtons, what was the acceleration? Okay, so once again, draw the picture, Newton's two laws, don't overthink it. So work on those, and later in the afternoon, I will upload the video with the answers, and good luck to you all. If you got any questions, let me know. Take care, folks. Bye.